Welcome to 4.4, tangent planes. We're going to start off by talking about gradients. And the first step is to write all our surfaces as level surfaces. And that's step 0 that you see here. Just move all the terms to one side. Then the gradient of big F is the vector formed by using the partial derivatives as the components of the vector. So the formula is right here. And the big fact is that big F is normal to the level surface. So it will be normal to the surface we have. So let's do an example. If f of xy is y cubed, find a unit normal to the surface at the point P. So f of xy is z, which I have written right here. So step 0 is to form a big F. Big F is move all the terms to one side, y cubed minus z. And then the surface will be defined by big F equals 0. Now we can form the gradient. Del F, pronounced del, it's an upside down triangle, and we want the partial derivative. So the partial derivative of big F with respect to x is 0. The partial derivative with respect to y is 3y squared. And the partial with respect to z is -1. All right, now del F at P is this point up here, is 0, 12, -1. That vector is normal to the surface that we were given. Now we want a unit normal, so we have to go one step further. The length of del F of P is square root of 12 squared plus -1 squared, which is the square root of 145. And to get a unit vector, we want, I'll call it V, we want del F at P divided by its length. So that's the vector 0, 12 over root 145, and -1 over root 145. Okay, now we can use the gradient to get equation for tangent planes and equations for normal lines. And here's how. Step 1 is to rewrite our surface as a level surface. That's what we did above. And step 2, since the gradient is normal to the surface, the equation of the tangent plane is defined here. And if we want the normal line, the gradient points in the direction of the normal line, so we can use the gradient as the coefficients of t in our typical formulas for the parametric equations of lines. All right, so let's do an example where we do both. We're going to find the tangent plane and parametric equations for the normal line, and here's our surface. So step 1, we need a big F. So big F, I move all the terms to one side. Typically I'll move the z over, but you could move it the other way. 2e to the x squared minus 2y minus z. Okay, now we're going to need del F. So del F, I want the partial with respect to x of big F, which is 2e to the x squared minus 2y times the derivative of the exponent with respect to x, which is 2x. And then for the partial with respect to y, I've got 2e to the x squared minus 2y times the partial with respect to y, which is -2. And then for the partial of big F with respect to z, I just get -1. So let's clean that up a little. 4x e to the x squared minus 2y, comma, -4 e to the x squared minus 2y, comma, -1. Now we need del F at P. P is up here, 482, and so that's going to be 16 e to the 0, so e to the 0 is 1, and then -4 e to the 0, so -4, and then -1. All right, so let's do the tangent plane first. We're going to use the use me every day formula for equations of planes. And in that use me every day formula, the big ABC is going to be 16, -4, -1. That's our normal. So we've got 16 times x minus x naught. X naught is 4. Minus 4 times y minus y naught, which is y minus 8. And then -1 times z minus 2. And that equals 0. Okay, if we clean that up, 16x minus 4y minus z equals 30. Now that's the standard equation of a plane. That's kind of how I like it. But in your homework, I've noticed they're going to ask you to solve for z. So they're going to want z equals 16x minus 4y minus 30. Okay, now we've done all the work, so the normal line's easy. Our direction vector is del f. So our direction vector is 16, negative 4, negative 1. And our x naught, y naught, z naught is the point we're given, which is 4, 8, 2. So we use the parametric equations for lines. That's x equals x naught, which is 4, plus, in this case, 16t. Y is going to be 8 minus 4t. And z will be 2 minus t. And that's it. So it all depends on finding the gradient. But don't forget, when you find the gradient, you need to do it of the correct function. And the correct function is big F. And you find big F by moving all the terms to one side. Okay, and that's the end of what I'm going to do with you. For your own reading, you're going to read about linear approximations and the linearization. And I did a worked out example here for you. But I just want to mention one thing. We found linear approximations back in single variable calc, and the linear approximation was simply the tangent line. So you can approximate any point on this curve here, as long as you stay close to the point where you find the tangent line. You can approximate any point on that curve with the tangent line. Now, we have an analogous formula for surfaces, but instead of using a tangent line, we use a tangent plane. And that's what the linearization formula is all about. Okay, and that is the end of this section.